This is the video 1 of MEKG video series. In this video, marine engineering materials topics are discussed. Topic 1. Mechanical properties of materials.
Ductility is the property of a material that enables it to be easily drawn into wire form. Brittleness is defined as lack of ductility. When a load is applied, brittle materials break without bending or deforming. Malleability is a property similar to ductility. If a material can be easily beaten or rolled into plate form, it is said to be malleable. If all the strains in a stressed material disappear upon removal of the stress, the material is said to be elastic. This is an essential property for materials from which springs and load-bearing structures are made. If none of the strains in a stressed material disappear upon removal of the stress, then the material is plastic. Plasticity is the opposite of elasticity and similar to malleability. It is the ability of a substance to be easily bent or shaped without cracking and without any harmful internal stresses being set up. The strength of a material is dependent on the amount of load that it can carry. The principal forms of strength in materials are tensile, compressive, shear, torsional, stiffness, and flexibility. Tensile strength is resistant to pulling or stretching forces. Compressive strength is the ability to support weight or resistance to squeezing forces. The toughness of a material is the ability of a material to sustain variable load conditions without failure. Materials could be strong and yet brittle. Tough materials have strength and resilience. Hardness is the resistance of a material to plastic deformation, usually by indentation or penetration. It is a measure of resistance to permanent deformation. The hardness of a material is determined by observing how far a hard steel ball or a pointed diamond will penetrate into the material. Hardness of a metal is increased by alloying, cold working, and precipitation hardening.
Topic 2. Steel and cast iron.
Steel is an alloy of iron and carbon. Pure iron is soft and ductile. Carbon is added to increase the strength of the iron. When 0.05 to 0.3% of carbon is added to iron, low-carbon steel is formed. Low-carbon steel is also called mild steel. It is used for making wires, sheets, nails, chains, rivets, and structural members. When 0.3 to 0.5% of carbon is added to iron, medium carbon steel is formed. It is used for making connecting rods, crankshafts, spline shafts, forging dies, and springs. When 0.5 to 1.8% of carbon is added to iron, high carbon steel is formed. It has high tensile strength and hardness. It is used for making chisels, drill bits, dies, springs, and metal cutting tools. When 1.8 to 4% of carbon is added to iron, cast iron is formed. It has high compressive strength, good machinability, and wear resistance. It is used for making engine cylinder heads, piston rings, valves, pipes, and pump casings.
Topic 3. Metallurgy of carbon steels.
Metals and alloys are crystalline solids containing randomly oriented crystallites or grains. Grain size and structure determine the properties of the metal. The three phases, ferrite, pearlite, and cementite, are the three principal constituents of the microstructure of plain carbon steel. Ferrite is pure iron, soft and ductile with considerable strength. Cementite is a hard and brittle compound of iron and carbon. Pearlite is an alternate lamellae of ferrite and cementite. This provides substantial strength to the steel. When carbon is added to steel, pearlite starts forming. The free ferrite is completely transformed to pearlite at 0.87% carbon. At 2% carbon, the cementite starts to form. At 6.67% carbon, the structure becomes fully cementite.
Topic 4. Iron-carbon diagram.
Iron is an allotropic metal, which means it exists in more than one type of lattice structure. In normal room temperature, lattice arrangement of iron is BCC. Whereas at 908 degrees Celsius, it changes to FCC gamma, and then at 1403 degrees Celsius, back to BCC again, and vice versa. Alpha iron is stable at lower temperatures, and gamma iron is stable at higher temperatures. The x-axis represents the percentage composition of carbon in steel, and the y-axis represents the temperature in Celsius. Pure iron melts at 1539 degrees Celsius. Cementite melts at 6.67%, and carbon melts at 1550 degrees Celsius. The steel begins to solidify when it reaches a temperature corresponding to the line ACD. Steels, containing less than 4.3% carbon, start precipitating austenite crystals, and at temperatures above 4.3% precipitate cementite. Austenite is the solid solution of carbon in gamma iron. Steel solidifies at temperatures along the line AECF. Steels containing 0.8% carbon and below solidify completely at temperatures corresponding to the AE line and consists only of austenite. Cast iron, containing 2 to 4.3% carbon, solidifies at 1130 degrees Celsius. Austenite crystals precipitate simultaneously with cementite to form ledeborite. These cast irons will consist of primary austenite and ledeborite crystals. Cast iron, containing 4.3 to 6.67% carbon, solidifies at 1130 degrees Celsius and consists of primary cementite crystals and ledeborite. After this primary crystallization, all steels consist of austenite and all cast irons consist of cementite and ledeborite. The secondary crystallization occurs in the solid state. The upper critical temperature line, GS, indicates the beginning of austenite decomposition and the precipitation of ferrite. The line SE indicates the temperatures at which austenite decomposes to form secondary cementite. Point S, corresponding to 0.8%, shows the minimum temperature at which the austenite can exist in equilibrium condition. At point S, austenite decomposes to precipitate cementite and ferrite at the same time. This results in the formation of pearlite. At normal temperature, hypoeutectoid steel will consist of ferrite and pearlite. Hypereutectoid steel will have a structure consisting of pearlite and excess cementite. On complete cooling, hypoeutectic cast iron will have pearlite, ledeborite, and secondary cementite. Hypereutectic cast iron will consist of ledeborite and primary cementite.
Topic 5. Heat treatment.
Induction hardening. It is a method of surface hardening of steels by using high-frequency electromagnetic field. The component is placed in the inductor. When an alternating current is passed through the inductor, it sets up a magnetic field. The alternating magnetic lines tread through the surface of the component, inducing an alternating current of same frequency but in reverse direction. The reverse alternating current passes along the surface of the conductor and is known as skin effect. When the desired temperature is reached, after a set time of 1 to 6 seconds for about 1,000 to 10,000 cycles per second, the surface is quenched by pressurized spray of water. Nitriding. It is the process of surface hardening by addition of nitrogen to the steel surface. Nitride promoting elements are aluminum, chromium, vanadium, or molybdenum. In nitriding process, the steel component is placed in a gas-tight container through which ammonia gas, NH3, is circulated. Container and the component temperatures are raised approximately up to 500 degrees Celsius, from 40 to 100 hours depending on the depth of hardness required. At this temperature, ammonia dissociates and nitrogen is liberated. The liberated nitrogen is absorbed in the surface layer of the steel. Nitrides are then formed close to the material's surface, promoting surface hardness. The case depth is about 0.025 to 0.05 millimeters. Surface hardness is around 1,000 to 1,100 Vickers. Hardening. The steel with 0.3 to 0.7% carbon is heated above 750 degrees Celsius to 900 degrees Celsius, depending on the carbon content, and then rapidly cooled by quenching produces hardened steel. The degree of hardness depends on the carbon content of steel, quenching media, and the quenching temperature. The quenching media can be caustic soda, brine, water, or oil, depending on the rate of cooling required. Hardening material in this way produces internal stresses and makes the material brittle. Tempering. Tempering is a process whereby the hardened steel can be partially softened in order to offset the brittleness. It leaves the metal hard and tough enough to do its job. Tempering consists of heating the material to some temperature below 720 degrees Celsius and holding this temperature for duration of time. This depends upon the mass and the degree of toughness required, and then quenching or cooling in air is carried out. The combination of hardening and tempering is greatly employed with steels and alloy steels to obtain the desirable properties. Straight carbon steels with carbon content below 0.2% are usually not subjected to hardening and tempering processes. Annealing. The objectives of annealing are grain refinement, inducing ductility, stress relief, or a combination of these. Castings, forgings, sheets, wires, and welded materials can be subjected to annealing process. In this process, the material is heated to a predetermined temperature depending on the percentage of carbon content, allowed to soak at this temperature, and then cooled in the furnace at a controlled slow rate. Normalizing. The objectives of normalizing are grain refinement to produce uniform structure, increase ductility, and to improve strength. The casting is heated to about 750 degrees Celsius to 900 degrees Celsius. It is held at that temperature for a short time and then cooled in still air at room temperature. The more rapid cooling of the material gives better, closer-grained surface finish. Normalizing differs from full annealing. The difference is that the rate of cooling in normalizing is more rapid, and there is no extended soaking period. Case hardening. This treatment is also called pack carburizing. The steel component to be case hardened is packed in a box made of fire clay, cast iron, or a heat-resisting nickel-iron alloy. Carbon-rich material such as charred leather, charcoal, crushed bone, and horn, or other material containing carbon is used as the packing medium, which is made to cover the component. The box is then placed in a furnace, and the temperature is raised above 900 degrees Celsius. The surface of the component will absorb carbon, forming an extremely hard case. Depth of the case depends upon two main factors, such as the length of time and the carbonaceous material employed. Actual case depth with this process may vary between 0.8 mm to 3 mm and requires between 2 to 12 hours to achieve, depending upon these limits.
Topic 6. Alloy steels.
The addition of nickel to steel imparts added strength with considerable ductility and toughness. Steel with 22.3% nickel is highly resistant to corrosion by hot gases and seawater. It has a low coefficient of thermal expansion. It is used for steel turbine blades, internal combustion engine valves, and for machine parts that are subjected to a wide range of temperatures. Chromium is added to steels which are to be heat-treated. It gives hardness, good wear resistance, and increases the tensile strength and corrosion resistance of low-alloy steels. Steels with 8% chromium are used in the manufacture of electrical equipment, and those with 15% chromium are used to manufacture springs, ball and roller bearings, and so on. Nickel-chrome steels are ductile, hardenable, and wear-resistant. They have good resistance to impact. Depending upon their composition, these steels can be mild, medium, high tensile, or self-hardening steels. The mild nickel-chrome steels are used in the manufacture of crankshafts and axles. Medium nickel-chrome steels are used in the manufacture of cranks and connecting rods. High-tensile nickel-chrome steels are used in machinery components. Self-hardening nickel-chrome steels are used in highly stressed shafts, tubes, gears, and so on. The addition of vanadium to steel improves the mechanical properties and increases the effects of other elements. Best results can be obtained by adding 0.1 to 0.2% of vanadium to nickel-chrome steels. It helps produce sound steel ingots and is excellent in removing oxides from steel. The addition of molybdenum reduces the temper brittleness of nickel-chrome steels or its tendency to become brittle when continuously exposed to high temperatures. This is used in making crankshaft. Silicon imparts strength and fatigue resistance and improves electrical property. It is used in making springs, valves of internal combustion engines, and so on. Tungsten provides softening of steels at high temperatures. These alloys are called high-speed steels as they retain their hardness up to 6,000 degrees centigrade. And intermittent heating to this temperature further hardens them. It is used to make high-speed cutting tools, permanent magnets, and so on. Manganese increases the hardness and tensile strength of steel and increases resistance to abrasion. It is used in making structural components. Plain carbon steels tend to crack during hardening. To overcome this problem, Alloy tool steels or non-shrinking steels, which contain high carbon, manganese, tungsten, and chromium, have been developed. Typical non-shrinking die steel contains 1.5% of carbon, 0.9% of molybdenum, 0.5% of tungsten, and 0.75% of chromium. As the amount of the alloying elements is small, this steel is not very expensive and is used for making dies and thin tools needing to be hardened.
Topic 7. Non-ferrous metals.
Copper. Copper is a reddish-brown, lustrous metallic element with a melting point of 1080 degrees centigrade. It has higher thermal and electrical conductivity. It is malleable, ductile, and machinable. It has good resistance to fatigue, abrasion, and corrosion. Applications: electrical conductors, heat exchangers, alloying. Tin. Tin is a silver-colored soft metal and has a melting point of 232 degrees centigrade. It is ductile to cold working such as rolling, extrusion, and spinning. It has good resistance to acid corrosion. Applications: coatings, alloying. Nickel. Nickel is a hard, lustrous white metal and has a melting point of 1450 degrees centigrade. It has a high tensile strength, good corrosion, and oxidation resistance. Applications: alloying, electroplating, permanent magnets, and thermocouple. Lead. Lead is a bluish-green metallic element which alloys easily with tin, zinc, antimony, and copper. It is twice as soft as iron or steel and melts at 326 degrees centigrade. It has a high resistance to corrosion and acids. It has low strength, hardness, and elasticity. Applications: storage batteries, pipes, and bearing metals. Aluminum. Aluminum is a white-colored light metal and has a melting point of 650 degrees centigrade. It is a very good conductor of heat and electricity. It has a high resistance to corrosion. It is malleable and ductile. Applications: structural components, engine parts, storage containers, shipping containers. Chromium. Chromium is a steel gray metal. It is mostly used as an alloying element. It is used as a protective coating of elements. Applications: turbine blades and valves. Zinc. Zinc is a bluish-white metal and has a melting point of 420 degrees centigrade. It is a brittle metal but has good resistance to corrosion. It is malleable and ductile. Applications: sacrificial anodes, coating on steel, die casting. Titanium. Titanium is an allotropic metal. That is, it can exist in two different crystallographic forms. It has a melting point of 1680 degrees centigrade, low thermal conductivity, low coefficient of expansion, and high electrical resistance. It has a high corrosion resistance. Application: plate-type heat exchangers. Molybdenum. Molybdenum is a metal that has a very high melting point of 2550 degrees centigrade. At high temperatures, molybdenum has good strength. Applications: metal spraying and turbine rotor.
Topic 8. Stress strain. Topic 9. Tensile strength. Topic 10. Cyclic loading.
A. Very low amplitude acoustic vibration. B. High cycle fatigue. Cycling well below general yield. Rho Y. C. Low cycle fatigue. Cycling above general yield, but below the tensile strength. Rho TS.
Topic 11. Creep test.
The objective of creep test is to calculate limiting creep stress. This test measures and records stress, strain, temperature, and time. The creep stress consists of applying a fixed load to a test piece and maintaining it at a uniform temperature. One platinum wire and platinum tube is spot welded to the specimen. The wire slides inside the tube and both contains reference marks. Elongation of reference marks are measured on the scale inside a telescope. The elongation of reference marks is recorded at the desired time interval for the entire duration of the test. The values are plotted in a graph to obtain the creep curve. The limiting creep stress of the material is calculated from the curve.
Topic 12. Periodic motion and oscillatory motion.
Periodic motion of a body is one which repeats itself at regular intervals. The motions of second and minute hands of a clock are periodic motions. The revolution of the Earth around the Sun is also periodic. Oscillatory motion is one in which a body moves to and fro about a fixed point. The motion of the bob and the simple pendulum is an oscillatory motion. The oscillation of a loaded spring is another example.
Topic 13. Damped and undamped oscillation.
A system oscillating with constant amplitude executes undamped oscillation. In this case, the energy of the system remains constant. If a system oscillates with amplitude decreasing with time, it executes damped oscillation. In this case, dissipative forces act on the system. There is a continuous decrease in the energy of the system. Hence, the amplitude decreases continuously with time.
Topic 14. Sonometer.
Laws of vibration of a stretched string are demonstrated using a sonometer. A sonometer consists of a hollow wooden box. A metal wire is fixed at one end, and the other end passes over a smooth pulley. The metal wire is stretched between two knife edges as shown. The wire is kept taut by adding weights at one end. A small paper rider is placed at the midpoint of the vibrating segment. A tuning fork of frequency N1 is used to excite the wire. The length of the vibrating segment is adjusted for resonance by moving one of the knife edges. The resonance is indicated by the fluttering and falling of the paper rider. Now, the length of the vibrating segment is measured as L1. The experiment is repeated with another tuning fork of frequency N2. The first law of vibration, namely NL is constant, is now verified. According to the second law of vibration, the vibrating length is proportional to the square root of the tension. Using a tuning fork of frequency N, the vibrating length for tension T1 is determined. Again, the vibrating length for another tension T2 is determined. Using these values, the second law of vibration is verified.
Topic 15. Vibration monitoring.
In this media, you are going to learn about vibration monitoring of marine diesel engine. The hull of the ship is subjected to vibratory influences arising considerably out of the diesel main propulsion on account of the following: guide force moments, transverse reaction forces acting on the X-heads due to the connecting rod or crankshaft mechanism, axial vibrations in the shaft system, torsional vibrations in the shaft system. The shipboard engineer should be sensitive to the indications of abnormal vibrations during the operation of the engine or other machines. Besides engines, the machines such as motors, pumps, compressors, gearboxes, belt conveyors, etc. involve the transmission of rotary mechanisms. These machines require bearings that support the weight of rotating parts and bear the forces arising out of their operations. Hence, vibration monitoring is normally done at the bearings of the common machines by placing accelerometers near the bearings. Mechanical vibrations. This type of vibrations originates due to the oscillatory movement of a mass about a reference position. This oscillatory movement is depicted in terms of displacement, velocity, and acceleration. Displacement is usually preferred for measuring low-frequency vibrations, such as machine imbalance. Measuring velocity provides a rational indication of the amplitude, that is, severity, of the vibration, and is therefore preferred for monitoring machine conditions. Acceleration is preferred for measuring shocks and high-frequency vibrations that may cause wear and fatigue. The vibration measuring instruments are of two types: peak indicating instruments used for detecting the transient vibration and shock, RMS indicating instruments used for detecting the effective RMS value with a selectable time constant for a steady indication. The RMS indicating instruments are mainly used for continuous vibration monitoring and are more informative than peak indicating instruments. The most extensively used vibration transducer is the piezoelectric accelerometer that produces an electrical output which is directly proportional to the acceleration of the vibration in a machine. A handheld machine condition detector captures and displays temperature, velocity, and enveloped acceleration, vibration, and alarms. Thus, you have learned about vibration monitoring of marine diesel engine.
Topic 16. Destructive tests.
Tensile test is carried out to ascertain strength and ductility of a material. The specimen is held in self-aligning grips of a tensile testing machine and subjected to a gradually increasing load. An extensometer is provided to give extension readings of the specimen while the load is gradually increased. With the values of the extension with respect to load, the stress-strain curve can be drawn. As the load increases, the specimen gets fractured. After breakage, the broken ends are fitted. The distance between the reference marks and the smallest diameter are measured. Hardness can be determined by Brinell hardness test. This test consists of indenting the surface of a specimen by means of a 10 mm hardened steel ball under load. Duration of load application is 15 seconds. The Brinell number is a function of load applied and indentation area. The diameter of the indentation is found by a low-powered microscope. Brinell number is given by the ratio of load and indentation area. The indentation area is measured by a microscope. Significance of hardness number is that it gives a measure of resistance to wear. This test is useful for determining differences in materials due to heat treatment that would not be indicated by the tensile test. A notched test piece is gripped in a vise and is fractured by means of swinging hammer. After the specimen is fractured, the hammer arm engages with the pointer, which is carried for the remainder of the swinging arm travel. At the completion of the hammer swing, the pointer is disengaged. The reading indicated by the pointer is the energy required to fracture the specimen. Usually, 3 tests are carried out on the same specimen, and the average energy is taken as the impact strength value. The objective of creep test is to calculate limiting creep stress. This test measures and records stress, strain, temperature, and time. The creep stress consists of applying a fixed load to a test piece and maintaining it at a uniform temperature. One platinum wire and platinum tube is spot welded to the specimen. The wire slides inside the tube and both contains reference marks. Elongation of reference marks are measured on the scale inside a telescope. The elongation of reference marks is recorded at the desired time interval for the entire duration of the test. The values are plotted in a graph to obtain the creep curve. The limiting creep stress of the material is calculated from the curve. A fatigue testing machine simulates the stress conditions developed in the machinery component parts by varying the cyclic loads. The magnitude of stress is changed in the machine. The setup consists of an electric motor capable of running at 10,000 RPM. An appropriate bearing which relieves the electric motor of the large bending moment. Chuck to hold the specimen. Rotating lever arm subjected to a downward force in order to place the specimen in bending state. The revolution counter measures the number of revolutions the specimen has undergone. Because of lever arm subjected to a downward force, the upper surface of the specimen remains in tension and lower surface remains in compression. While the specimen is rotated at higher speeds, at any given position, the specimen is subjected to alternate compressive and tensile stresses. The test is carried out on similar specimens of the same material at different loads, and number of stress reversals to fracture the specimen is noted. The results are plotted on a graph from which fatigue limit is calculated. Logarithmic scale is adopted to condense the graph. This test is carried out by bending a straight specimen of plate to 180 degrees around a former. For the test to be satisfactory, no crack should occur at the outer surface of the plate. Significance of this test is that it is carried out in boilerplate materials because boiler is a fired pressure vessel.